Physics Part 256. Planet and Satellite Orbits. Most planets in the solar system have orbits which are nearly circular. Planets and satellite orbits. Mostly planets in the solar system have orbits which are nearly circular. We now bring together the idea of gravitational force and that of the centripetal force to derive a relation between the period and the radius of the orbit of a planet describing a circular path about the Sun and a satellite moving around the Earth or another planet. Consider a planet of mass m in circular orbit about the Sun of mass m. If the radius of the orbit is r, the gravitational force F GRAV between Sun and planet. So the gravitational force is equal to Gm m over r square. By Newton's law of gravitation, it is the force that provides centripetal force as the planet moves in its orbit. The centripetal force F is given by the F circ is equal to mv square divided by r, where v is the linear speed of the planet as has just been stated. F gravitational is equal to F circular. Thus, Gmm over r square is equal to mv square over r. The period of t of the planet in its orbit is the time required for the planet to travel a distance 2 pi r. It is moving at the speed of v, so v is equal to 2 pi r over t. Putting this into equation above, we have Gmm over r m into 4 pi square r square t square divided by r, or simplifying, t square is equal to 4 pi square divided by gm whole square into r cubic. Another way of writing this is t square over r3 and a pi square divided by gm is equal to t square over r cubic. Look at the right hand side of this equation. The quantities r pi and g are constants. If we are considering the relation between t and r, the planets in the solar system, then m is the same for each planet because it is the mass of the Sun. This equation shows that for planets or satellites describing circular orbits about the same central body, the square of the period is proportional to the cube of the distance, and that's how it moves all along. And it has got its radius as well. For planets or satellites describing circular orbits about the same central body, or the square of the period is proportional to the cube of the radius of the orbit. This relation is known as Kepler's third law of planetary motion. Johannes Kepler, 1571-1630, analyzed data collected by Tycho Brahe, 1546-1601, on the planetary observation. He showed that the observation fitted a law of the form t square and r cubic. 50 years later, Newton showed that an inverse square law of gravitation, the idea of centripetal acceleration, and the second law of motion gave an expression of exactly the same form. Newton cited Kepler's law in support of his law of gravitation. In fact, the orbits of the planets are not circular but elliptical, a fact recognized by Kepler, the derivation of simpler for the case of circular orbit. Table collects information about T and R of the planets of the solar system. The last column shows that the value of T squared divided by R cubic is indeed constant.